Hey, physics friends, and welcome to 16.2, the wave nature of light. We're going to talk about today, why do we see in color? What is color? Like you're looking at a screen right now. How is that screen making color? Maybe you read a book or you picked up some product that had paper and it had a logo or advertising. How do they make color on here? Is the color that they make on here the same as the color that the way that you're seeing the light from this screen right now? We're going to talk about those things. And it's kind of complicated, but it's really fascinating. And let's get started. To get us going today, I have, this is a USB microscope. And it's got its own little light source. And I can show you what it's seeing right now. You can see me over here. But I want to specifically look at that magazine I just showed you for a second. This Wired magazine. And we're going to zoom down into it. We're going to go look right at the printing, real close up, to see how it makes its color. You might think that they just use green ink to do that. You wouldn't be correct. Turns out, here's the green ink that you were seeing before. And I'm going to zoom in one more. It turns out that printers, maybe you popped open your printer before, at home. Printers only have 4 colors of ink: cyan, magenta, yellow, and black. Those 4. And you can see them all right here. The cyan are those light blue ones. The magenta is the red-ish. Yellow, and then the black. So you can make any color that humans can perceive with these 4 colors right here. So if I kind of scroll across this, they just vary the intensities of which ones they're showing, which ones they're not showing, to make all the different colors in this veritable rainbow. Now, I'm going to turn this back on the computer screen. So I'm going to turn down the lights, and I'm going to put it on the screen of my computer so you can see how the pixels themselves are made here. So I'm going to zoom in. Let's get it right side up so you can maybe even see. So there it says March, M-A-R. And you can kind of see what's happening. I'm going to zoom in and you can see the pixels. Right? So we're using red, green, and blue. So I think almost everything that makes color on a screen uses RGB color pixels. A red pixel, a green pixel, and a blue pixel. And you can just see that they turn them on and off at different intensities to make the different colors. If you turn them all the way off, you get black. And if you want to get different colors, if you want red, then you only turn the red one on. If you want blue, then you only turn the blue one on. And if you want white, you actually turn all of them on. So if I zoom this out, you'll see that this is actually white. Right here. Whoop, that's the white section. The white section is just turning all pixels on. Right there. Let's talk about how you actually see color. I've got an interesting video that goes through the biology of how we see color, why we see color.
You might have heard that light is a kind of wave, and that the color of an object is related to the frequency of light waves it reflects. High-frequency light waves look violet, low-frequency light waves look red, and in-between frequencies look yellow, green, orange, and so on. You might call this idea physical color, because it says that color is a physical property of light itself. It's not dependent on human perception. And while this isn't wrong, it isn't quite the whole story either. For instance, you might have seen this picture before. As you can see, the region where the red and green lights overlap is yellow. When you think about it, this is pretty weird. Because light is a wave, 2 different frequencies shouldn't interact with each other at all. They should just coexist, like singers singing in harmony. So, in this yellow-looking region, 2 different kinds of light waves are present. One with a red frequency, and one with a green frequency. There's no yellow light present at all. So, how come this region, where the red and green lights mix, looks yellow to us? To understand this, you have to understand a little bit about biology, in particular, about how humans see color. Light perception happens in a paper-thin layer of cells, called the retina, that covers the back of your eyeball. In the retina, there are 2 different types of light-detecting cells, rods and cones. The rods are used for seeing in low light conditions, and there's only one kind of those. The cones, however, are a different story. There are 3 kinds of cone cells that roughly correspond to the colours red, green, and blue. When you see a colour, each cone sends its own distinct signal to your brain. For example, suppose that yellow light, that is, real yellow light with a yellow frequency, is shining on your eye. You don't have a cone specifically for detecting yellow, but yellow is kinda close to green and also kinda close to red, so both the red and green cones get activated, and each sends a signal to your brain saying so. Of course, there's another way to activate the red cones and the green cones simultaneously, if both red light and green light are present at the same time. The point is, your brain receives the same signal regardless of whether you see light that has the yellow frequency or light that is a mixture of the green and red frequencies. That's why, for light, red plus green equals yellow. And how come you can't detect colours when it's dark? Well, the rod cells in your retina take over in low light conditions. You only have one kind of rod cell, and so there's only one type of signal that can get sent to your brain, light or no light. Having only one kind of light detector doesn't leave any room for seeing colour. There are infinitely many different physical colours, but because we only have 3 kinds of cones, the brain can be tricked into thinking it's seeing any colour by carefully adding together the right combination of just 3 colours, red, green, and blue. This property of human vision is really useful in the real world. For example, TV manufacturing. Instead of having to put infinitely many colours in your TV set to simulate the real world, TV manufacturers only have to put 3, red, green, and blue, which is lucky for them, really.
So we learned from that video that our eyes have roughly 3 different types of cells to detect color. One gets stimulated when it gets hit with red, one gets stimulated when it hits with blue, and the other one gets stimulated when it gets hit with green. And getting hit with red and green light is the exact same thing as if yellow will stimulate them as well. So your brain can't make a distinction between getting red and green at the same time or just pure yellow. And this gives rise to the idea of colors by addition. And you saw that when I would hold this up to, and I'll do it again here. So just looking at your computer screen, you see how this is green right here. So I'm going to take my microscope and I'm going to go right up to it, and you can see that the way that this computer screen makes green is by only turning on the green pixels. It makes red by only turning on the red pixels. It makes blue by only turning on the blue pixels. But how does it make yellow? You'll see right here, if I zoom in, I'm on the yellow right now. It's the red and green turned on simultaneously. So if my red and green are turned on, your brain interprets that as yellow. And if I go up here to the cyan, it's the blue and the green pixel. And if I go over here at magenta, it's the red and blue. But if I go in the very middle, you'll see it's white, and that's the red and the green and the blue. So we call this color by addition. We're adding together different wavelengths in our eyes to make the different colors that we perceive. Now, making color with pigments is a little bit different. You saw this magazine that I used here, and pigments are a little bit different. If you've ever popped open the hood of a color printer, you'll notice that there are 4 colors inside of there. There's a cyan, magenta, yellow, and black. These are called the primary pigments, and let me explain to you why. So I've got a little visualization here. Follow me up to the board. So let's say the sun, and for all intents and purposes, the sun is white light. Even though the sun looks yellow and the sky looks blue, we'll explain that in a little while. But when you've got white light, which is red, green, and blue, we've already discussed that. How do you standing here, this looks red to you. What the red pigment does is it absorbs blue, it absorbs green, and it reflects the red into your eyes, and that's why it seems red. This is why when we talk about paints, we call it color by subtraction, because the red absorbs blue and green. And the same thing is kind of true over here if we shine light on green, and here's you, green is going to absorb blue, and it's going to absorb red, and it's going to reflect green. Green absorbs red and blue. And going over here to blue, blue does the exact same thing. Blue is going to absorb green, absorb red, and reflect blue. So blue absorbs red and green. Now, you get down here to black. Black is the absence of color. So black absorbs all of them, which is why black gets the hottest. It's absorbing the most energy. Black is the absence of light. And white does the exact opposite. White reflects everything. If you shine white light on it, it's going to reflect all that. If you only shine blue light on something that is white, it's only going to reflect the blue light, so it's going to look blue to you. The same is true up here. Like if we were to only shine, let's say, red light. Let's say we had shined red light onto this green surface. Since green absorbs red, it's going to absorb everything, it's going to reflect nothing, and it's going to look black. It will physically look black, and that's what this picture, it kind of represents right here. For instance, here's red light, and you can see that this is a green dice right here. So if you have red light on something that absorbs red, that red is being absorbed, and so it reflects nothing. And the absence, and you see how this looks black. And they're doing it with blue light over here. So you can see like how these colors are interacting with one another to absorb different things. Let's talk about down here, cyan, magenta, yellow, and black. We'll take me again, and we'll take my colors. What does yellow do? Now, you know how we see yellow, and we talked about that just a second ago, that yellow is red and green. Yellow absorbs blue. Cyan. We see cyan because we're seeing green and we're seeing blue. We're absorbing the black. Cyan absorbs green and blue. And you might be able to see a pattern here. We go over to magenta. Take my incident colors. Magenta is red and blue. It absorbs green. Oh, it just absorbs green. So, I misspoke here. Cyan absorbs red. Oh boy, I got a little crazy here. And yellow absorbs blue. So I've got one that absorbs blue, one that absorbs red, and one that absorbs green. So this is why we call these the primary pigments. Because what if I wanted to mix yellow? I take yellow, and then I'm going to mix it with cyan. I'm going to mix these two things together. Their properties are going to combine because yellow, you'll notice that yellow absorbs blue. So if I put these things here, the yellow part is going to absorb the blue. The cyan part is going to absorb the red. So what they both reflect, you'll see that they both reflect the green. That's what they share in common. So this, cyan plus yellow is going to equal green. And you can see this in this color wheel right here, that cyan plus yellow equals green. Cyan plus magenta is equal to blue. Yellow plus magenta is equal to red. This is how we call it color by subtraction, because when you combine cyan, cyan absorbs red. And then you're going to combine it with yellow, and yellow absorbs blue, so you're taking red away, you're taking blue away, and then you're left with green. We call this colors by subtraction. And the primary pigments are yellow, cyan, and magenta. And that's why you saw them on this magazine right here. So here's that red from my magazine, and we talked about just a second ago that to get red is yellow plus magenta. So I'm going to zoom in on my red down here, and you'll see a bunch of yellow and magenta dots. This is how they make that. Sometimes they don't. You know, I'm going to go to a different red, and they actually just looks like they flooded that. If you look at any consumer packaging at home, anytime you throw something away, you'll see little boxes like this. These are the colors of ink that they're using on this box. So I click on here. So here, and you'll see cyan, magenta, yellow, and black. CMYK on a lot of these different packages. Just to show, and they can tell. These are proofs, so when you're printing your thing, if one of these circles doesn't print out quite right, then you know that's the ink that's missing from the printing press. So they print these little proof stickers here so they can tell which colors are running low if something doesn't print out quite right. Let me highlight one more thing here. This yellow, it gets a little bit complicated. Take a look at the yellow dice. And you know that yellow, what does yellow do? In order for us to see yellow, we need to see red and we need to see green. That's how we get yellow. Yellow absorbs the blue and it reflects the red and the green. So what if I only shine blue light on it right here? Take a look at it. You can see right there that since yellow, it's absorbing the blue, if you put blue light on it, it absorbs it and it makes it look black. This is why it's important. I don't know if you guys are getting dressed in the morning. It depends what color lights are above your head. Like if you have yellow lights or white lights, or there's a little bit of tinge to your colors, and that's what makes things look a little bit different color than they're supposed to be. Color filters. Filters work kind of in the same idea, is that they let certain colors pass through them. For instance, a red filter here, and this is my filter, and I've got colored lights. A red filter lets red light through it, and it won't let blue and green. And likewise, a blue filter will let blue light through. And a green filter will let green light through. Now, what about a filter like yellow? Now, remember, for our eyes to see yellow, we need red and we need green. That's how we see yellow. So a yellow, it blocks blue. Maybe in recent years, a lot of people have been looking at their screens and they've tied a human being's circadian rhythm, because we're used to rising with the sun, going down with the sun, but now we're staring at screens so much. And so when the sun goes down, we want to block that blue light, so you'll put on yellow tinted glasses, like they call them blue light glasses. And if you look through them, there's a little bit of a yellow tint to them because the yellow will block the blue. Cyan. A cyan filter. Now remember, to see cyan, we need blue and we need green. So what cyan does, cyan blocks the red. And magenta is the same thing. Magenta is going to block, I think, the green. Because in order to see magenta, we need red and blue. So then we're going to block that green one. Then we get into like, what if you look at something through a filter? You know, like what if we're looking at a, oh boy. Here's a good picture. I mean, it really exemplifies this point. Here's a yellow filter, and here's a magenta filter. But when you look through them both, right here, you'll notice that this looks very red. And remember that a yellow filter allows red light to pass through it, and it allows green light to pass through it. And a magenta, it allows red light to pass through, and it allows blue light to pass through. But what do they both allow? They both allow the red, and this one, the magenta one's going to block the green, and the yellow one's going to block the blue. So what do they both let through? They both let the red one through. And over here with the green, you'll notice like right here, in this sector, this looks green. Because remember, yellow is going to let red and green. That's how we see yellow. It lets red and green through. And then this cyan one is going to let blue and green through. So this lets blue, this lets green through. But what do they both share? They both let the green light through. And that's why we see green right there. Right? Looking at objects. I mean, well, just talking about color filters, maybe you've seen like a 3D image before. Maybe you've seen people wear those glasses that are like red and blue on each side, but that's how they're working. They're filtering out. So on the red side, your red is going to make this look, you're going to make that look black because it's going to filter it out. Your blue light side, it's going to filter out the red and make that look black. So each of your eyes can see a separate image, and you get that stereoscopic effect. One last thing, kind of going back to my filters. Why do certain things look the way they do? Let's give you an example. What if we're looking through a yellow filter, but we're looking at, let's say, a blue star, right? And what if the blue star is being illuminated by white light? Okay, so a blue star is going to reflect blue. It's going to absorb the red and green. But then my filter, remember, a yellow filter allows red and it allows green to pass. So it's going to block the blue. So this, to me, this star is going to look black. Like when we look at it through a yellow filter, it's going to look black. Now, go to a red star. Like if I was illuminating this with white light, so this is white light because it's red, green, and blue. So the red one is going to reflect the red. And then this is going to let the red pass, so that is going to look red to you because the red will get there. But let's say I'm not illuminating it with white light. Let's say I'm illuminating this blue star with black. I'm sorry, not black, but I'm illuminating it with blue light. And the red, it's going to absorb that blue, so it reflects nothing. And remember, the absence of color is black. So this star, when you observe it, it's going to look black to your eyes. A red star being illuminated by blue light through a yellow filter. There's so many different possibilities in understanding why do we see red, green, blue, yellow, magenta, and cyan? Because of addition. What do pigments do? Cyan, magenta, yellow, each pigment absorbs other ones. This whole idea of color theory is the purpose of 16.2. Thank you.